As recently as 1990, we hadn't yet discovered a single planet around another star beyond our solar system. When we thought about finding an inhabited world out there in the Milky Way, we had only the worlds of our solar system: Earth, Venus, Mars, Neptune, Titan, Pluto, Enceladus, Triton, and Jupiter's moons to consider as potential analogs. Now in 2025, however, we're closing in on an incredible 6,000 confirmed exoplanets, and we've learned that the most common type of world that we know of isn't represented at all in our solar system, a class of worlds known as super-Earths and mini-Neptunes. These exoplanets, often rich in atmospheric hazes, are the most abundant species of world known at present. Could some of these haze-rich exoplanets have something remarkable within their atmospheres? Are they rich in organic molecules? Do those molecules undergo a complex series of chemical reactions? And could there be even biological processes taking place? Even here in the JWST era, we're still struggling to make unambiguous sense of the observations that it's acquiring of these alien worlds. However, through combining the results available from laboratory work, new, advanced theoretical modeling, and cutting-edge observational data, scientists can learn to disentangle the various possibilities from one another. For the first time, thanks to a pair of new papers led by Dr. Chao's research group, we're coming to understand what observations of organic hazes on these common sub-Neptune worlds actually have the potential to reveal to us. It's vitally important to understand, from a scientific perspective, the pieces of evidence that we can bring together to help us in the quest to figure out what's present and what's happening in the atmospheres of alien worlds. The biggest driver of this field is the observations that we have. We can only draw conclusions based on the data that we collect. And the data that we collect is limited by the technologies that we've developed and the tools that we've built to find and analyze the types of worlds we're interested in. To find an exoplanet, the most successful methods have leveraged examining the light from a star that might house them. As the planet orbits the star also moves, or wobbles in its own orbit, due to the equal and opposite gravitational force that the planet exerts on the parent star. If the planet, star, and our line of sight to it are all aligned, then once per orbit the planet will pass in front of the star's disk, blocking a portion of the parent star's light. And if we can detect both of these effects together in the same star system, then we can infer the planet's radius, mass, and orbital period all at once. For thousands of exoplanets now, we've done precisely this, detecting planets ranging from super-Jupiter-sized all the way down to sub-Earth-sized, including planets of all sizes in between those two extremes. Unsurprisingly, the most massive planets were the rarest type of planet that we found. As we went to lower and lower mass ranges, we started to find greater abundances of planets. There were more Jupiter-sized planets than super-Jupiter planets. There were more Neptune-sized planets than Jupiter-sized planets. There were more sub-Neptune-sized planets than Neptune-sized planets. But among these sub-Neptunes, almost all of them are larger than Earth. Only a small fraction of the known exoplanets are approximately Earth-sized at all. Somehow, the most common, most abundant size of known exoplanet is in between the size of Earth and the size of Neptune, a super-Earth or mini-Neptune, which is a species of planet not found in our solar system at all. This isn't necessarily because Earth-sized planets are rarer than planet of super-Earth/mini-Neptune size, but rather because the telescopes and observatories that we use to find exoplanets are limited in their scope to find the smallest size, smallest mass exoplanets. There may yet be a greater abundance of Earth-sized or even worlds of sub-Earth, for example Mercury-like sizes, than even the super-Earth or mini-Neptune exoplanets, but it will take a superior generation of planet-finding telescopes to reveal those planets to us. What's kind of remarkable, though, is that even among these in-between worlds, the ones larger than Earth and the ones smaller than Neptune, they possess a bimodal distribution. There are the super-Earth worlds that are largely close in size to Earth, without volatile-rich gas envelopes, and the significantly larger mini-Neptune worlds, which possess large gas envelopes, rich in hydrogen and helium, surrounding them. Why is there such a stark difference between these two sets of worlds? We have to resort to theoretical modeling to understand why this may be. A second, independent of observation tool that we have to understand these exoplanets and their atmospheres. The leading idea is that it's all about planetary temperature driven by the proximity to their parent star. Young stellar systems, the ones that are still actively in their planet-forming phases, are going to form planets around them that pull as much material onto them as possible. The lightest elements, hydrogen and helium, will only remain around a newly formed planet in great abundance if those planets are both cold enough, or form far enough away from their parent star and massive enough or with enough gravity to hang on to those elements from the time those planets form until the present day. Although Neptune-like worlds and larger can maintain large, volatile-rich gas envelopes even close in to their parent star, the border between super-Earth worlds and mini-Neptune worlds appears to be consistent with being shaped by these two factors. If you're only a little bit more massive than Earth, you can still hang on to a large envelope of hydrogen and helium if you're far enough away from your parent star, at temperatures of a few hundred K or below. But if you get hotter than that, your hydrogen and helium gets blown away, and you won't be mini-Neptune-like at all, you'll be more Earth-like, or what we might rightly call a super-Earth world. Now that we're in the JWST era, we've begun to perform the incredibly important science of transit spectroscopy on many of these sub-Neptune-sized exoplanets. When an exoplanet relative to our line of sight passes in front of its parent star, the star's light doesn't simply get 100% blocked by the disk of the planet. Instead, if that planet also has an atmosphere, you'll find that the unblocked areas of the stellar disk continue to shine and emit light as normal. The areas of the stellar disk that are obscured by the solid surface of the planet are 100% blocked, but in the in-between areas, where the planetary atmosphere lies between the stellar disk and our line of sight, that light filters through the planet's atmosphere, leading to a variety of possible observational outcomes. You can imagine an atmosphere that's completely transparent to all light, but in reality, atmospheres are made up of atoms and molecules, and so there will be absorption signatures that show up in the spectroscopic data. When we break the observed light up into its individual wavelengths, we can alternately imagine an atmosphere that's completely opaque to all light, where the atmosphere is so thick, dense, and haze-rich that 100% of the light does indeed get blocked. But again, most atmospheres will be in between these extremes, enabling us to detect a mix of transmitted starlight and absorption features that correspond to the different species of molecular hazes that are present. That's where the third aspect of studying exoplanet hazes, laboratory experiments coupled with further theoretical modeling, comes into play with such great importance. What we can do, laboratory-wise, is to take an initial set of chemical compounds and to subject them to a variety of temperature and pressure conditions, leading to the synthesis of various additional, often more complex compounds. We do this in the laboratory to serve as an analog of what happens within these exoplanet atmospheres, including, within the presence of various heavy elements, aluminum, silicon, magnesium, etc., with atmospheres of varying compositions, nitrogen-rich, carbon dioxide-rich, hydrogen-rich, etc., at varying depths in the atmosphere from practically atmosphereless zero-pressure conditions up to or even in excess of one Earth atmosphere, and with a variety of temperatures, representing different distances from their parent star and different depths within the exoplanet atmospheres. This type of laboratory data is invaluable for comparing what we'll see when we observe these exoplanet atmospheres with what we infer is actually present within them. Where the conditions differ between these exoplanet atmospheres and the types of conditions we're capable of recreating in the lab, we use further theoretical modeling to bridge those gaps. Now, with that as our background and us all on the same page, we can look to the results of these two new scientific research works. Led by Professor Chao He of the University of Science and Technology of China and his graduate students Sai Wang, Haixin Li, and Zhengbo Yang, and including contributions from several researchers from the United States and France, these two papers focus on a common type of exoplanet, sub-Neptunes, distinct from the smaller super-Earths, that possess atmospheres rich in carbon dioxide. The closer a sub-Neptune is to its parent star, the less of its hydrogen and helium it can hold onto, leading to particularly CO2-enriched conditions. The question the researchers attempted to answer is simply, what types of hazes form in the atmospheres of such exoplanets? For a long time, people simply followed the work of researchers in the 1970s, including Carl Sagan, who studied the worlds in our solar system, and assumed such exo-atmospheres would have similar hazes to Saturn's giant moon Titan. But Titan has different conditions than the atmospheres of these exoplanets, in particular being significantly colder. To understand hotter exoplanet atmospheres, we need to use laboratory synthesis and theoretical modeling of the formation of these hazes, and then and only then, can we hope to make sense of these observations? They first performed laboratory simulations of carbon dioxide-rich gas mixtures at two different temperatures, 300 K and 500 K, both of which are temperatures of interest for the transiting exoplanets we see. When they subjected these gas mixtures to plasma irradiation, similar to what an exoplanet experiences in close proximity to its parent star, they found that both temperature scenarios led to the formation of complex organic hazes, with a variety of organic functional groups appearing when they performed a compositional analysis. However, the high temperature and low temperature scenarios led to different haze formation pathways, with the 500 K scenario leading to greater numbers of double and triple bonds, such as carbon-carbon and carbon-nitrogen bonds, larger average molecular size and molecular weight for the haze particles that formed, and greater abundances of nitrogen in their hazy molecules compared to the cooler 300 K scenario. However, both of these scenarios resulted in the copious production of complex organic hazes, including molecular formulas that match compounds essential to life processes such as nucleobases, sugars, amino acids, and more. This is a fascinating find, as these conditions were considered part of the graphite stability regime, where graphite-rich exoatmospheres are expected to produce only flat spectra, not the feature-rich spectra that would appear if organic hazes were present. These results will prove incredibly useful to exoplanet scientists all over the globe because, as Chao put it, these haze measurements provide the first data set tailored to CO2-rich atmospheres, critical for making sense of JWST's flood of new exoplanet data. The second paper, led by Chao's graduate student Hazy Li, went a step farther and directly measured the actual optical properties of haze particles and compared them with the optical properties of graphite. After all, if a sub-Neptune exoplanet contains ingredients that could lead to metal enrichment in their atmospheres, under the combined influences of photoevaporation and core-powered mass loss, it should be possible to make either organic hazes or inorganic graphite depending on a combination of factors. Although many have favored the production of graphite condensates on thermodynamic grounds, laboratory findings indicate otherwise, showing that organic hazes rather than graphite are produced at low pressures and at temperatures between 300–700 K. Exoplanets that possess such conditions could distinguish between the organic haze and the graphite haze scenarios, as organic hazes exhibit strong absorption features at 3.0, 4.5, and 6.0 microns, all observable with JWST, whereas graphite would be a constant absorber across all wavelengths. At shorter wavelengths, both would produce flat, featureless spectra, akin to what Hubble has seen for various sub-Neptunes. It leads to two interesting, potentially observable scenarios for transit spectroscopy of exoplanets similar to, for example, the famous mini-Neptune GJ 1214b. Strong absorption bands in such a mini-Neptune could indicate organic hazes present in carbon-rich atmospheres, but broadband absorption, such as with graphite, could lead to radius overestimation, as a thick graphite haze in an exoatmosphere would be indistinguishable observationally from an exoplanet with a much larger solid radius. As both Chao and Hazy Li emphasized, there is a population of superpuff exoplanets that has been hitherto unexplained, planets only a little more massive than Earth but larger in radius than Neptune. Understanding that a hot exoatmosphere would be large and inflated in size, and that graphite would absorb practically all of the starlight impacting that atmosphere if there were a high-altitude layer of it, represents a fascinating scenario for explaining the features of these planets. Both organic hazes and graphite can be present within a mini-Neptune's exoatmosphere, but which one dominates depends on a variety of factors that, only now, are being uncovered for the first time. Perhaps as Chao put it, some alien worlds appear so mysterious because their skies may be filled with thick organic smog, not unlike Titan's, obscuring the view. While most of the focus for life on planets beyond our solar system has focused on Earth-like analogs, perhaps an alternative bet is on these mini-Neptune worlds, as this new research suggests that alien skies may be full of hazes, many of which are likely to be organic-rich, than astronomers, astrobiologists, and planetary scientists had previously thought. After all, the first robust detection of an inhabited exoplanet isn't likely to come from one revolutionary eureka moment, but rather by building up a sturdy science case bolstered by multiple independent lines of evidence. By studying exoplanet hazes in this three-pronged fashion, With observations, laboratory synthesis, and theoretical modeling, one more tool for investigating these alien worlds is bringing our view of the universe into better focus.